This video lecture is meant to cover the information in Chapter 8, Section 3, which involves using Lewis structures to help you determine shapes of molecules. And from that, we're also going to be able to determine the polarity of the molecule. So if you're doing this lecture in the classroom, you'll have access to model kits. But since you're watching this on video, my guess is that you don't have an access to a model kit. So the model of that particular molecule is being demonstrated for you in this picture right here. So this is Br2. Each one of these orange atoms represents a bromine atom. And if we were to draw the Lewis structure, we would know that bromine has an electron dot structure with 7 valence electrons, but it's Br2, so we need to show 2 of those. And so we would actually write the Lewis structure from these 2 electron dots to end up looking like this. You would replace this pair of bonded electrons as a dash, and all the lone pairs would still be shown as pairs of electrons, pairs of dots around the 2 BRs. Now, if you look at this Lewis structure, you can see here that there is, we're going to count the number of bonding areas on the central atom. Now, there is no central atom because this molecule is diatomic. There's no one atom that's in the center of all the others. So we can consider either one of these bromines. So if we look at this bromine, we want to determine the number of bonding areas on this atom. So this particular molecule just has 1 bonding area. And if you also focus on this bromine, we're now going to count the number of lone electron pairs on this atom. So you can see here that there's 1, 2, 3. There are 3 lone electron pairs on that atom. If we were to draw this as a 3-dimensional drawing, it's not a very exciting 3-dimensional drawing because it is a 2-dimensional, really in reality a 2-dimensional molecule. So it's just Br-Br. Notice that we've dropped the lone pairs of electrons around the outside. Now the geometric shape of this molecule, it is indeed linear. 2 atoms, you can only ever have a linear molecule. Now to determine if this polarity, if the molecule is polar or not, we're going to bring out this chart, which you should have access to. If the molecule is linear, you have to then ask yourself, are all of the outside atoms identical? Well, the outside atoms are both bromine, and so yes, they are identical, which means that this molecule will be nonpolar. And that's because the electronegativity will be the same for both bromines, and they're pulling equally on that shared pair of electrons. So what we see here is that this is a nonpolar molecule. The next molecule that we're going to analyze is water. We see here that water has the formula H2O. You can see this is the oxygen. These are the 2 hydrogens. We can see here that if we were to draw the Lewis structure from the electron dot structures, we would have 2 hydrogens, each with 1 valence electron. And we would have 1 oxygen with 6 valence electrons. So you can see here that this is where we're going to have 1 covalent bond between this hydrogen and this oxygen, and then there'll be another covalent bond here. So if we were to draw this over nice and neatly, we would just have dashes where the shared pair of electrons are. But the 2 lone pairs of electrons do still have to be indicated, and you see them here as green dots. Now there is a central atom here, it's oxygen, and if you look at the oxygen, you will notice that there are 2 bonded areas around it, each going to a hydrogen. And there are also 2 lone pairs of electrons around the center atom. Now this 3-dimensional drawing is also fairly dull because it is a planar molecule. It is, it lays flat on a desktop, like you can see here in this picture. So we just draw it as the diagram is shown here without the electron pairs, the lone pairs. The geometric shape of this molecule, based on the 5 that we learned in the previous lecture, is that this is a bent molecule. Now if we bring out our chart, if it's a bent molecule, its regardless of whether the outside atoms are identical or not, the molecule will always end up being polar because of the bent structure. The bent structure implicitly creates a polar, asymmetrical distribution of electrons. The next molecule we're going to analyze is, this is methane Ch4. This is an example of a tetrahedral molecule. If we were to consider the Lewis structure, first take a look at the electron dot structures for the carbon and the 4 hydrogens. And you can see here that there will be 4 lines coming out of the carbon atom. And there won't be any lone pairs of electrons to draw because all the electrons are participating in covalent bonds. There are 4 bonding areas around that central atom, and there are no lone electron pairs around that carbon. Now here's where the 3D drawings get to be a little interesting, because on paper, when you draw the Lewis structure, it looks flat. But you can see here from the molecular model kits that it very much is not a flat molecule. And so this is where I'll ask you to draw this 3-dimensional drawing. Start with the carbon, start with the C. Draw a triangle coming to indicate that the bond is coming out at you, with a hydrogen at the end. Then you'll draw 2 hydrogens connected by dotted lines. Those are the bonds that are going away from you. And then the hydrogen going straight up connected by a line, that's the hydrogen that's going straight up and down. Now, to consider the polarity of this molecule, it is a tetrahedral molecule, and the question is, are all the outside molecules, are all the outside atoms identical? In this case, hydrogen, 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 so the answer is yes. And if that's the case, it will end up being a nonpolar molecule. The electrons will be distributed evenly around this molecule. So this ends up being nonpolar. Oh, and it looks like I have a typo there. That, of course, should say nonpolar. The second to last molecule that we're going to analyze is Ammonia Nh3, and this is what it looks like when it is bonded. There is a little cap here. This little cap is meant to indicate the lone pair of electrons that you'll see here when we construct the Lewis dot structure. So here's the nitrogen with its 5 valence electrons. Bring in the 3 hydrogens with their single valence electron. You can see that this nitrogen will have 3 covalent bonds, and it will have a single lone pair. So the Lewis structure is simplified like so. And as we just said, there are 3 bonding areas on the central atom of nitrogen. And there is 1 lone electron pair on the central atom of nitrogen. Now, this is another 3-dimensional drawing where you'll need to draw the hydrogen coming out at you and 2 nitrogens going away from you. Nothing will be coming out the top because that's an electron pair that we do not show in the 3-dimensional drawing. This geometric shape of this molecule is trigonal because of the triangle shape here, but it is trigonal pyramidal because it's not flat on a plane. So trigonal pyramidal. Now the polarity on this molecule, if we consult our chart, it's trigonal pyramidal. Regardless of what the outside atoms are, if they're identical or not, trigonal pyramidal molecules will always be polar. And again, like the bent molecules, because of that bent structure, because it's an automatic asymmetrical distribution of electrons because the atoms themselves are so asymmetrically distributed. So this ends up being a polar molecule. The last molecule that we're going to analyze in this lecture is formaldehyde, which this is definitely the most complex molecule we've looked at to date. What we have here is a carbon double bonded to an oxygen, and then there are 2 separate hydrogens also bonded to the carbon. So if we were to do a Lewis structure, we'll start with the carbon because it's in the center of this molecule. Remember, carbon has 4 single dots around it. We will bring in 1 hydrogen on one side of the carbon. We'll bring in a second hydrogen on another side of the carbon. and we'll bring in the oxygen on the opposite side of the carbon. And you can see that this will be a bond and this will be a bond, so two pairs of electrons are being shared between the carbon and oxygen, so that's where we get the double bond from. And if we take a look at the Lewis structure and clean it up, this is what we will end up with. A C double bonded to an O. The O will have two lone pairs of electrons on it, and the carbon will have two hydrogens coming out from the center. So now we really need to focus on the central atom of carbon. If you look at the carbon, I see that there are three bonding areas. One to the hydrogen here, another to the hydrogen down here, and one bonding area to the oxygen. So bonding areas are irrespective of whether it's a double or a triple bond. It's considered the double or the triple bond is considered to be one bonding area. Now, continuing to look at the central atom of carbon, you'll notice that there are no lone electron pairs around that carbon. And if we were to try to draw this as a 3D drawing, it's essentially a planar molecule, so we don't have to worry about dotted lines or funky triangle lines. So this is one way to do the 3D drawing. C double bonded to an O and two hydrogens coming out of the carbon. The geometric shape, this is a trigonal. You see the triangle right here. Trigonal planar because all four atoms are on the same plane. And if we consult our diagram right here, this is a trigonal planar. What we need to look at are the outside atoms. Are they identical? We have a hydrogen, hydrogen, and an oxygen as the outside atoms, so they are not identical. So that's going to set up an asymmetrical distribution of electrons, which in the end is going to make the molecule a polar, covalently bonded molecule. So this concludes our lecture on Lewis structures and geometric shapes of molecules, and you're going to get to continue exploring this in the classroom where you'll be working with the model kits and constructing new molecules and determining what their Lewis structures are, their geometric shapes, and their polarities. So we'll see you in the classroom.